Yeah.
Okay.
Yes, we can.
Okay, so thank you very much to the organizers for the invitation. It was really my pleasure. And I must tell all of you that Mahesh sir has really given a nice, a flattering introduction to me, but he was the person who first showed me that you can actually do simulations on a computer when I was 16 years old. So he was the person who started me on this journey. So it's really my pleasure to come here on his invitation and talk to you all. And in fact, the notebook that I'm going to show you today uses the technique that he showed me the very first time. And I must say, when I started to write this notebook, it all just came back to me without even having to look anything up. So it really made an impression on me when he first showed it to me. Okay, so let me start my presentation now. Okay, all right. So can you see the screen of my Jupyter Lab?
Yes, ma'am.
Yes, ma'am.
Okay, great. Thank you very much. All right. So today we are going to start with something very basic. And what we're going to do is, since uh, Pratik and Jigar have been showing you how to use Python notebooks, we are going to essentially start simulating some physics problems using Python notebooks. So to start with, we are just going to do a little bit of gravity. And yesterday, I know that you already did this in using Excel. So you probably, so it's probably quite fresh in your mind what we are trying to do. So hopefully, as a start, this will not be very difficult. Okay, so just a couple of notices before we start. So first of all, feel free to interrupt me at any time if you have any questions. And secondly, I understand and speak both Hindi and Marathi as well as English. So if any of you feel like your English is not good enough and you can't ask a question in English, please feel free to ask it either in Hindi or Marathi, and I'll be able to answer you as well. Okay, so let's start uh, looking at some things with gravity. All right. So are there any questions before we start? Okay, good. So yeah, so the first cell that you see in front of you is essentially just some initialization cell where we are going to import some things that we might need later on. So forget this decimal; it's not important. This line ensures that all the figures that you plot are seen right there in the notebook. And then there are some parameters for the figure that I've put there just so that the labels are big enough so you can see it on your screen when I share. Okay. So I believe this notebook will be shared with you for you to download and to play with. But if you can also open your own and try some things along with me, I think that would be great. And in the afternoon, you will have actually more time with your tutors to figure out all the small things related to these Jupyter notebooks. Okay, so to start with, what we are going to do is we are just going to learn how to implement all the integration techniques that you've learned. You've learned Euler method and so on in Python. So you've done it before using Excel. So now we are going to do it in Python first. So, and the example that I've chosen is the simple harmonic oscillator. Okay, so remember the simple harmonic oscillator has only one equation, which is a second order differential equation, which is d2x by dt squared is equal to minus kx squared, right? So what we want to do is we want to sort of split it up into two. There's going to be one equation for dx by dt, which we call v, and one equation for dv by dt. So this is a normal way of solving a second order differential equation where you can split it into two first order differential equations. And we've seen yesterday already how to do this, right, using Euler's method. So we need some, so since it's a second order differential equation, we need two initial conditions. We need an initial condition for x and for v. We're going to set some parameters a time step for our integration, which I call dt, which I set here to 0.1. And you have this spring constant for your harmonic oscillator k, which is given as some number. And the main thing that you need is essentially the position of the oscillator, that is the x, and the time. That's the thing that we're going to plot, right? So these are two lists that we're going to fill as we do the integration. Okay, so that's the first thing we do. Okay, so then this is simply the Euler method, right? So you're going to integrate over some time range, so which I here set to be 500. It's just an arbitrary number that I chose based on the parameters so that we can see what we're doing. Okay, and then these are the equations that we know very well. So you know that x1, which is the next time step, is set by x0, which is the current time step, plus v0 times dt. So what you did yesterday. Then you set the acceleration as minus kx. So I'm using here, if there is a mass, I'm using units mass equal to 1. Okay, so this a is set simply by k. And then you can set the new velocity using the old velocity plus acceleration times dt. Okay, so this sets up your new time step. And what you do is you append your x that you've calculated to your x list, the time that you've calculated to your time list. So there are multiple ways of doing this. So in this example, what I've done is this range goes from 0 to 500. It's an integer number. And your time is essentially this integer times dt. So it starts from 0 and 500 times 0.1 is 50, right? So it goes from 0 to 50 in steps of 0.1. So that's one way of doing. You could have also done it using an addition method, which we'll do later on maybe. Okay, and then when you want to go to the next time step, your what is now your new time step becomes your old time step for both the position and the velocity, right? So this is the simplest Euler method that you can write, which you can run. And then using the plot, you can just plot your x with time. And just to remind ourselves which one is time and which one is x. So we say that the x level is time. And you can plot it. And this is what it looks like. So it's as expected, right? It's a simple harmonic oscillator. Okay. So now just to get ourselves into the spirit of things, I'm going to ask you, how would you determine what is going to be the maximum amplitude of this object? And I believe this was touched upon yesterday. So anybody has a guess of what determines the amplitude?
Come
on, just take
position, maximum displacement.
Yes, that's what I'm asking you. What determines the maximum displacement? How would you calculate what the maximum displacement is?
So remember, from the graph. From the graph, no.
From the graph, you can maybe, yes. But but what I want you to sort of see is that we have these two initial conditions, right? So there are two ways of initializing the simple harmonic oscillator. Either you set the amplitude and put the velocity to 0, which is what you did yesterday, or you can set your amplitude to 0 and the velocity to the maximum velocity. Right? Both of these are equivalent ways of initializing your harmonic oscillator. So normally you set your maximum amplitude. So when you have the velocity, how would you find out the maximum amplitude? Even without looking at the graph.
Velocity is 0.
Yes. What happens when the velocity is 0?
The displacement is maximum. So
yeah, you're just repeating the same thing over and over again. So okay, so let me give you the
Energy
answer.
conversion.
Exactly. Yeah, I mean, yeah, obviously you know the answer, but yeah, right. Yeah. So it's energy conversion, right? So what happens at the maximal point is that all of your energy is potential energy when you are at the maximal amplitude. And when you're at the amplitude of 0 and maximal velocity, all of your energy is the kinetic energy. So the way you find out your maximum displacement is that you calculate your maximum kinetic energy, which you know based on this. And then you ask at what value of x will you have the same potential energy. That is how you get your maximum amplitude. Okay, so you can do this with pen and paper and check that this maximum that you get from the graph is indeed the same number. So that is why I wanted to ask you. So the main thing that I want to convey to you by these lectures is that often when we do physics with pen and paper, it seems something like we are only doing for exams or for pen and paper, right? But when you start using computers, especially to model real life, uh, it really gets into you that what you are talking about is reality, is the real world. So that's what we want to essentially convince ourselves with increasingly more complicated physics things that we're going to learn. Okay, so there are some questions that you can go through with your tutors later on. And so again, for period, so you can of course determine it using your equations. You can also determine it using this graph. So you can try several things just to get your hands on how to do this kind of programming with Python. Okay, so let's now get into the meat of this method. Okay, so what we're going to start with is to try and do simulate the effect of gravity, starting with just 2D, so just x and y plane, right? Without going through the third dimension right now. Okay, so so again, let's start. So this is the first example that we have. So assume that you have two masses, one which is very heavy and one which is very light. And we know what happens when you have a case like this, that the lighter one is usually one that moves the most. It's moving around the heavier one. And based on the velocity this object has, you have different kinds of orbits. Okay? Or maybe not even an orbit, you just have some kind of trajectory which may be parabolic or hyperbolic and so on. So what we're going to try and do now is to sort of look at all of these possibilities. Okay, we're going to use the Euler method that we just saw for doing this. And well, let's start. So since now we have x and y, so you need dt, of course. You need x0 and y0, which is going to be your initial location. So forget the values for now. We are going to change all of them and see what happens. And you have to set some x and y velocities. Okay. Then you want to set the location of the heavy mass, which for our simplicity, I've just set to be at the origin. And then there are some masses for the heavy guy and for the light guy. Okay. And also, just to make our calculation simpler, we're not going to work in SI units because it just makes, it means that you have to keep track of a lot of big numbers. So what we're going to do is we're going to work in units where g is equal to 1. So everything is, you can write it in terms of these kinds of small numbers that we can work with. Okay, you can always convert things to SI units if you want. All right. So then again, we have some initialization of x, y, vx, vy, and time. Okay, and the equations look almost exactly the same. Okay, the only thing that you need to understand is how. So because now you have two directions, the main thing that you need to understand is how do you split your vector of your acceleration, which has a direction, remember, in the x and y directions. Okay, and this is the trick for that. Okay, so so if you can calculate this particular quantity, which is the x value of so let's call the heavy mass the star and the small mass the planet. Okay, so the x value of the planet with respect to the star, and similarly the y value of the planet with respect to the star, that will give you the x and y directions, right? And to normalize, you're just going to divide it by the total r. So the distance the planet is from the direction. And this is what is going to give you your x and y components of your acceleration. Okay. So your acceleration is essentially given by the mass of the heavy object divided by r squared. This is just your gravitational law. And then the x and y components are given in the following way. Okay, so this is the main crux that you need to understand. Everything else is just Euler's method. So let's go through this step by step again. Okay, and the first thing you do is you know that you have some velocity that you get either from the previous iteration or from your initial conditions. You can set your x1 and y1 based on that. You can ignore this for now, we'll come back to it. Then you calculate your r squared and your distance in x and y. Okay. Then what I've done is I've essentially set that the star has a certain radius. Okay, so this is radius 100. So if you hit the star, then you're going to stop. So that's another braking condition that you have. Yeah, and then you calculate the acceleration, the x and y components of it. And now that you have the acceleration, you can set your new velocities based on the acceleration. Okay, so again, this is vx0 times ax times dt, and similarly for y. So now all of your things are done. You can append your x1 and y1 and your time, and you can set your old step values to all the new step values. So when you loop over, so the reason for, so when you loop over time, this old values become 1, and so when it comes back again, your x0 is going to be what x1 was the last time, right? So this is how it works, and we can run this. Okay, and yeah, so we can make some plots. So first plot that you can think of making is x and y with time. Okay, and there is some value here. Let's increase the time. Okay. Oops, what happened? Ah, there we are. Sorry, I just forgot to initialize the masses. Okay, good. Okay, so you can just plot the x and y with time, and it doesn't look like anything that is familiar to us. The only thing that you can perhaps notice, maybe we can increase the time step, the time again. And the only thing that you can notice from here is that it seems to be periodic. Okay, so x and y are periodic. And if you want to actually see something that is familiar, then what you need to do is plot the trajectory. Okay, so instead of plotting x with time and y with time, what we are going to do is we are going to plot x and y. Okay, so this is the only main thing that you need to plot. So let's maybe make a new. Okay, and you can see that it looks like an ellipse. Okay. So since I have a lot of these, oops. Okay, right. So you can see that it's an ellipse, and just to make it look nicer, I've set some other things. So I've set, for example, the x and y limit. I've made this plot into a square. So these are all sort of decorative things that you don't really have to do. Okay, it's just so that things will look nicer. And because if you just plot this, then you don't know where the original star is. So I've put a circle with the original star there. Okay, so remember we had r square, we said that break if r square is less than 100. So the radius of this planet has to be square root of 100, which is 10. So I've put a circle of size 10 over there so that you can see where the star is. So this is what it looks like. And you can see that it is an elliptical orbit. Okay. So what we can do now is we can play with some different velocities. So let's say, so we started with 40. So okay. So first let us look at what the location that we have set. Okay. So we're starting with x0 equals 0 and some non-zero y0. Okay. So that simply means if you have a star, then the planet is located in our XY system just above. Okay, so there is no X displacement, there is only Y displacement. And because because I wanted to just show you the effect of the transverse velocity, I've not given it any velocity in the Y direction, because it's only in the X direction. So I've set this to 50. If you set it to 50, for example, and you rerun, let's look at this one, and you plot the trajectory, and you see that it's now perfectly circular. And this is also something that you can calculate simply by hand, right? So for a particular, again, what you do is you essentially set your kinetic energy, which is half mv squared, to your potential energy, and that gives you the velocity that is needed to be in orbit at that particular location, right? So that gives you these values, and you can check out different things. So you can also give it a non-zero y velocity and ask what happens. And what happened? Oh, there it is. Okay, so it was not enough. Let's make it a bit more drastic. Okay. 40. Okay. So it just went out. Okay, that was probably too drastic. Okay, something like this. Okay, so you can play with this and try to figure out different kinds of orbits. Yeah, so there are some exercises of what you can do, which you can try out later. Okay. Right. Yeah. So so this is essentially the answer.
Possible to see a condition where I mean it starts from the aphelion point, so you are given very small velocity and it comes very close.
Okay, let's try. All right. So let's see.
50 0 it was circular, right?
Mm-hmm. Yeah.
Velocity.
So let's see.
Make it.
Maybe we can start with smaller number 10, and then we need.
No, position can be same, right? Position.
Yeah, but then
Okay.
it's just yeah. Anyway, let's try what happens here. What is this? Oh, let's do small. Okay. Okay, you started here. You want to start somewhere over here. Let's see. It's around 30. And now it will take some time to calculate what this X and Y will be.
Let us do it this way. You know, we go back to the circular orbit, the original numbers.
Okay, let's do that. So this was 40, and we had 50 and 0.
Yeah. So now.
Okay,
Okay,
Yeah.
this is circular. So now instead of giving critical velocity, give smaller velocity at the
Okay.
same location.
Yeah.
So
Right.
instead
So we
of
can give
keep that
40.
40, no, why
Oh, yeah, sorry.
take it
Yeah.
closer? Yes.
Yeah, yeah.
Just
No, I
make
got it.
this, yeah.
Yeah. So, okay. So one more thing that is happening here is that because you're using the Euler method, it's not really accurate enough. So that is why you see that there is some precession that is going on. So we need to go to either Rungakutta or something a bit more accurate to get this right.
Or we may take dt very small. That will
Yeah,
help.
we can do that as well. Then we need to integrate over a larger time. Yeah, much better. Yes. Okay, so you want to make it even more elliptical?
But now that we are keeping, I think 40 as the initial position, maybe keeping something like 100 as initial position and then giving low velocity will make it nice elliptical. Is it
Yeah,
possible to
actually, yeah. So
show
there were other
starting point?
options.
Yeah, that is the
There are other options here actually.
okay.
So I
Okay,
wanted
okay.
to show you that. So
Let us
maybe we
go to
can.
those. Yes, yes.
Yeah.
Let us go to
So
those.
yeah. So let's go to those. So right. So are there any questions right now before we go to the other options?
Ma'am,
Yeah.
I have one question.
Uh-huh.
Like we were changing x and y velocity and the position values in x and y direction. Like how
Yeah.
we are making sure that we will get ellipse or circle. Is it purposefully or it is just a random settings to get the ellipse or?
It is not random at all. That is the whole point, right? So once you set
I'm
your
not
initial
getting like
velocity,
uh,
that is what
like
physics
what to
does.
change and to get the ellipse or.
Once you set your initial velocity and position, that determines completely what your orbit is going to look like. You don't have to tell anybody that this you should make it into an ellipse or make it into a circle. Right? That is the physics insight that you get from doing this example. That if you start with a velocity that is smaller than the one required for exact circular orbit, which you can get by equating half mv square to mgh, then you get something that is not a circular orbit.
Okay.
Right? So that is the insight that you get. You don't have to set anything by hand. Okay, more questions?
Thank you, ma'am.
Yeah, sure. And you don't have to
Ma'am,
thank me, by the way, every time I answer.
There is a question here
Yeah,
on
yeah.
the chat. Could you show some? There is a question on the chat. Could you show some orbit which is completely different?
Yes, we are
Like,
coming to that. We're going to look at elliptical orbits. We're going to look at escape velocities. We're going to look at hyperbolic trajectories and so on. Yeah. There was another question from someone.
yeah, ma'am. Ma'am, here you have written PLT.GCA. So what does
Yes.
that function?
Yeah. So basically, so this is the way you add a circle. So this is the circle that I've drawn here.
Okay, for that star.
Yeah, yeah. So
Okay.
you define what a circle is, and this tells the plot that it should add this patch that you've defined earlier. So you could have any patch that it could have been a square or some kind of more complicated object, and you say plot.gca dot add patch, and you can give whatever that patch is. So then it will show it on the plot.
Ma'am, that size of the circle is controlled by the tan or in that.
Yes, yes. So these are the coordinates, and this is the size.
Okay.
Right. Okay, good. More questions? Okay. All right. So this was so this is the calculation for what velocity you require for orbit and what velocity you require for escape. So that's those are the numbers, and we can try them out. Okay. So before we go there, what I'm going to do is, which is something that we're going to also use later on, is we are going to write a function, okay, that does this one step of Euler integration. Okay, so remember what we had was we had this time loop, and we did the step, and then we set all this t0 to the new value of t and so on. So this step is useful because when you have multiple particles later on, it will help us generalize, and you will see how it helps. So what we're doing is simply using exactly the same thing as before, except now just we have a function for doing each time step. Okay, so if you give it initial values of x, y, vx, vy, and whatever maximum t max, it's just the maximum time that you want to run over. Then it just does the same Euler integration. So it's exactly the same thing, copy paste it, right? And it returns the new xy. It should actually have returned also vx, vy. Right. So the reason I wanted to do this was essentially to get different kinds of orbits at the same time. Okay. So what it did was it did this Euler integration over this full time range that you supplied for a given velocity vx, vy in the initial velocity. Okay. All right. So we were trying many different options. So we're going to keep the position the same, 0, 40, and we're going to change the x component of the velocity that we give to different values. So there's 30, 57, 60, and 70. Okay. So these are the options, and we're going to run it over a time of 100. Okay. And then the only thing that I've done is plotted all these 4 different kinds of trajectories. So let's run this. Okay. And you can see that these are, this is what is happening. So in the first case, where you had only 30, okay, then your horizontal velocity is not big enough to make it into any kind of orbit, and it eventually crashes into the star. Or you can, in fact, now we can change our words to say that this is a planet and we are trying to launch a satellite. Okay, so if you want to launch a satellite, if it doesn't have enough horizontal velocity, then it's just going to crash back into the earth. Okay. So then we can start 57. So you can see for this particular case, 57 gives you an exact this kind of orbit. Then you go to 60, and your orbit is even more elliptical. And then you can give 70.7, which you can calculate as the escape velocity. And this guy, essentially, so this is a parabolic orbit, and this guy is going to escape. So it's never going to come back. Okay, so
Hello, ma'am.
So these are, yeah.
Ma'am, can a function return more than one value? Like you have written
Yes.
this x comma
Yes.
y.
So in Python, you can do this. In C or Fortran, usually it returns just one object, but in Python, you can return as many objects as you like.
So this is the format. Return x
Yeah.
comma y and whatever we want. Okay, thank you.
Exactly. Right. Good. So yeah. So these are the various kinds of orbits possible. You can also do something which is even stranger, which is something called a slingshot. So this is usually what is used when you want to send missions to, say, the outer edges of the solar system or so on, where you can't possibly just using using the propulsion that we have on Earth, make it have high enough um, velocities. So what you do is you try to slingshot it around either the moon or some other planet that is going to come along the way, and that way it gets a boost of even more velocity. Okay, so that's essentially what you can think of as a hyperbolic orbit. So in this case, so this is how we start. So in this case, it's starting from x of 100. So that's the upper edge corner here, and it has and y0, and it has some x velocity and y velocity. So I just played around till something nice came around. So you can play with these things and find some nice numbers that demonstrates what you're trying to do. Okay, so you can do this, and you can see. So it's everything else is basically pretty much the same. And you can see what the slingshot looks like. Okay, so it came from here. Since it's coming from the top, your y velocity is negative. It's going in this direction, so your x velocity is also negative. So that's these minus 60 and minus 20. And it basically gets deviated because of the gravity of this heavy object here. Okay, so these are the different kinds of orbits that are possible and that you can play with more during your tutorial sessions. Okay, so yeah, so then we are going to go to the second case. So right now we basically made a very simple assumption that this heavy object is so heavy that you can assume that it's completely stationary, and it's only the satellites that get affected. However, in realistic phenomena, of course, even the light object affects the heavy object. It's usually just too small for us to see. But if you have two objects of the same mass, say you have, say, a binary star system, or you have, if you've been following the news, there have been a lot of reports lately about these gravitational wave signatures from mergers of neutron stars or black holes and so on. And in these cases, of course, both objects affect each other and sort of revolve around each other, right? So that is actually the real thing that you need to do, is to assume that all masses affect each other and to figure out how you can calculate this full system together. And once you've been able to do this, you can generalize this to any number of objects that you may have in your system. Okay, so that's what we're going to do next. Before we go there, are there any questions about these orbits? Okay, good. All right. So to do that, remember what we need is that rather than just having one x1 and y1 equation, you want to be able to write these x and y equations for each mass independently. So here is where Python is really super helpful. So you don't have to say for particle 1, x1 equals x0 plus vx0 plus times dt. Then for the second mass, again, you have to write the same equation. You don't have to do that. What you can do is you can turn your x and y, and similarly vx and vy, into arrays. So did you work a little bit with arrays when you learned about Python?
Yes, ma'am.
Okay, good. So essentially, you can just think of them as column vectors. And another useful thing that works with Python is that you can actually just do your mathematical functions over arrays like you can normally think of when you're writing your equations. So if you were doing this in C, then you would have to write a for loop over all the elements of the array and do this kind of integration. In Python, it's just much easier. Okay. So yeah, so this is essentially exactly what we are doing before. The only thing that changes is now the potential that you get. So we don't know how many particles there are. So I said 2, but they could have been 10, right? So for each pair of particles, you're going to have a potential that you need to calculate. So if you want to calculate the motion of this guy, and there are 2 other heavy objects around, you need to figure out what the potential is because of this guy and what the potential is about because of this guy. And because we are working in this XY coordinate system, you can always sum up all the X components and you can always sum up all the Y components, right? So that's how, because that's how forces work. If you have 2 different forces, and you sum them up, you sum up the X components, that gives you the total X component, you sum up the Y components, that gives you the total Y component. So that's essentially what we're doing. It's exactly the same thing as before, only now, instead of just for one particle, you're going to sum over all of the particles, okay? So you're going to sum over the whole array. One way of doing that is to take an index that runs over the range of the length of that array, okay? And for each particle, you need to calculate its combination with every other particle. So that is why you need another for loop, which also runs over the array, length of the array. Okay. So now in our case, the length of x1, x0, and all of them are just the same, right? So you can choose either one as your length. The only thing that you do is if you know that the particle is not going to affect itself, right? At least in this picture, and especially your R is going to be 0. So if it had affected itself, then your contribution would have been infinite. So you're going to ignore that contribution. So if your I is a particular value, then the particles that it interacts with are all values other than I. So you say if I equals J, you continue. That means you just skip the loop and go ahead. And then you simply calculate the X distance and Y distance as before. You calculate the R squared, and you calculate the acceleration, and similarly calculate the X and Y component of the acceleration that this particle has from every other mass. Okay, so this is what this function is doing. It is calculating the contribution to the acceleration from every single mass that is out there. Okay, and then finally, once you have the total acceleration, which is at the end of this for loop, then you're going to essentially calculate the new Vx's, which is just Vx0 plus Ax times dt as before. Okay, and what this step does is instead of just returning x0 and y0 as before, it also returns rather x1 and y1 as before. It also returns vx1 and vy1. Okay, so the new x, new y, new vx, and new vy. Okay, so then what you're going to do is you can have multiple steps of this, and each time you set the old to new and get a new step. You set the old to new and get a new step. So that's essentially exactly what we did before, but now it's completely general. So you can do this for any number of masses. Okay, so let's try it out with a binary system, and then yeah, is there a question? Okay, so let's try it out with a binary system. Okay, so let's say you have 2 stars. Both of them have x value of 0. That means they are on the y-axis. And they start with y values of plus and minus 20. Okay, so they are essentially on the y-axis. One is at plus 20, one is at minus 20. And they have some non-zero velocities in these directions, okay, or rather the other direction. So the top one has a velocity of plus 2, the bottom one has a velocity of minus 2, and they don't have any y velocities, okay, and they have the same mass. So this is the simple binary system that you can plot. So we're going to plot them using 2 different ways. So one way is going to using the scatter plot, which is what I want to do, because I want to show you in each time step where the dots move. Okay, and then we are just going to save the values that we get from each time step into an array and then plot that array together to see the full orbit. Okay, So let's try and do that. All right. Okay, good. So let's do that, and let's do it for a small range. Okay, let's do it for a range of 20. Is there some dt? Yeah. Okay. Another thing that I should tell you. So for this, I said dt default to be 0.1, but when you call the function, you can set dt to a different value. So if you call the function without having any dt, then it assumes a dt of 0.1. Okay. So this is how you give default arguments to a function. Okay. So all right. So this is our binary system. So the way you call it is like this. So you want x1, y1, bx1, by1 to be the output of your time step. Okay. And the time step takes in x0, y0, vx0, vy0, and the masses of the objects and dt. Okay. And then you're going to plot, one guy is going to be plotted in green, the other guy is going to be plotted in red. And then you set x0 to be x1, similarly for the others, and repeat for whatever time range you have. Let's try. Okay, so you can see that they have moved a little bit. Let's do it for bigger range. Still working. So you can see that this is what your orbit looks like. Let me put dt to be a high number. Well, it wasn't accurate enough. Okay, that was not a good idea. So you see what happens when things are not accurate enough is that every time you calculate, there is a little bit of error. And then at some point, things really go haywire. So if you have something like this, some weird thing that comes out, then it always helps to ask whether there is some numerical inaccuracy in your calculation. Okay, so let's stick with 0.1. And because you're plotting a circle at each time, you can see that these are actually quite blobby. But we also saved the values of the arrays. So you can plot those arrays, and you see this is what the orbit of a binary system looks like. So you have this entwined orbits, which works. Let me do something else. So for this, since we are between 30 minus 30, let me set this to much smaller. Okay, looks a bit better. Okay, let me also do one more thing. If t so I'm only going to plot every 10th guy. Okay, so I'm not going to plot every single case that comes out. I'm only going to plot every 10th. So did you do the percent function or other percent operation when you did Python?
Yes, ma'am.
Okay, good. So this is the remainder. So you only basically are going to pick 0, 10, 20, and so on. So, okay. So now you see what I was trying to show you was essentially how the two stars move, essentially, right? And you can see that they are much closer here. So remember, the time step is the same in each case. So here it is moving much slowly because in the same time step, it is moving only a little bit. Whereas here you can see big gaps for the same time step. So here it is moving fast. So what this tells you is that when they are close, they move very fast, and then they go farther apart, and then they're closer, and then they move fast, and then so that's how they go. Okay. All right. So this is what your binaries look like. You can again check. This is the same. All right. And the advantage of writing our function in this simple way, where you could take any number of masses and calculate the total potential contribution, is that now you can go to a trinary system with exactly the same function. You don't need to write a new function every single time. Okay. So before we go there, are there any questions?
I mean, Ma'am, can you please explain that again? The changing of value, like getting to know where it is fast and slow moving by changing that modulus of
Okay.
percentage.
All right, sure. Right. So basically, what we're plotting, remember, is essentially what happens after a time step of 10, right? So let's say our units here are days. Okay. So what happens after every 10th day? Okay. So look at this X. You can see my mouse pointer, right?
Yes, ma'am.
Yeah. Okay. Good. So when you're in this extreme range, so even after each 10 days, it's only moved a little bit, right? It's moved little. However, here you can see that every 10 days it moves a lot. What that means is that the speed here is very small and the speed here is very large. Similarly for the other guy, except it's just diametrically opposite. So it's slow here and it's fast here. So what is happening here is that when you're at the edge, the star is moving slowly and then it suddenly whooshes past the other star. So when they're close together, their gravitational attraction is much higher, but they do have some velocity with respect to each other. So they whoosh about very fast and then they go farther apart. But they're still in a bound system, so they don't go away infinitely, but they slow down and then they eventually come back again.
So basically, changing 10 to 20 would only reduce the number of points in the graph. Just the gap of days will increase.
Yeah, exactly. So
Okay.
these arrays that we print, that they actually have every single time step. So I just put this as 10 because then you can individually see how they are moving. But you can
Okay.
also just plot the whole orbit, and this is what that looks like.
Okay.
Okay, more questions? Okay, good.
Ma'am,
So then, yeah.
ma'am, what does that set aspect mean? You have written that x is set
Ah,
aspect 1.
yeah. It just means that your plot is a square plot. So remember the plots that we had earlier? This, for example, did not have an aspect ratio of 1. Aspect ratio is essentially the x times y measurement of the plot.
Okay.
Okay. Yeah. More questions?
Yes, there are two questions.
Hmm.
One is how to know the position of, say, star A with respect to star B.
Okay.
And there is other question. If we change the masses, can some star leave the orbit?
Yeah, so you can do a lot of things. So I just showed you the simplest system. Let me copy this and then we can play with it. Okay. Okay. So all right. So what I did was I took a very symmetric system, right? Both of them had the same mass. Both of them were essentially equidistant from the origin, and they had opposite velocities. So what you can do, for example, is give one of the guys a different velocity, and you can ask what it looks like. Okay? So what is happening here now is because one of the guys has an overall velocity, the whole system is going to get pulled in that direction. Okay. So then that's what we look like. So the first question that you had, what is the distance between the two stars? You can always, of course, calculate it. So let's make an array called x dist, y dist. Okay, and we know what. So okay. So in this case, we know that there are only two objects. So this is not fully generic. It only works for this binary system. Okay. So let me put this. Works only for this binary system. Okay. So you can say x dist dot append absolute value of x10 minus x11. The brackets, right? And similarly for y. Okay, so let's go back to the original case where you first had a symmetric system, and then we'll do the asymmetric one. Okay, so you have this x dist and y dist. Okay, so it's running. Let me add one more thing here. And do we have a time array? Okay, let's just forget x dist. So yeah, so this is what the x and y. Oh, it's not very nice. Okay, let me do it this way.
Remove the absolute function, no?
Yeah, I wanted to keep that because I wanted to do something else.
So
Yeah, we'll try
absolute
with that as well.
only one.
R. Sorry.
That absolute may make a problem.
No, it's fine. I just wanted to actually plot the R. That's why I had the absolute.
Okay.
It's let's see. We'll have to make. Okay. Maybe I change this here. Oops. What happened now? Sorry. Okay. So this is what I wanted to show you essentially. So what it is telling you is that the distance between the stars follows a periodic distribution as well, right? So after each certain number of time, it comes, it goes to the farthest point, and at some points it comes to the closest. So we can actually run it for a bit longer. So let's run it for 400. And yeah, so now you can see that the distance itself is also periodic. Okay, so that perhaps answers the first question. What was the other one? I forgot. What happens if you have a different?
Yes.
Different.
Is it possible to have different mass?
Yeah,
which
absolutely.
can escape.
Yeah, I mean you can have a whole lot of things. So I haven't tried this out. So we just have to play with it and figure it out. So let's just start by changing.
Question from the chat. So these are the questions from the chat.
Yeah, thanks.
And we can also play with this in the afternoon tutorials. So that is also possible.
Yeah. So see, what is happening is that if one of the particles is heavier, then it sort of affects the other particles. So so it's still a periodic system, but the amplitudes go up and down. And so yeah, so you can play with it and ask what happens with different cases. Okay, so you can change the masses, you can change the velocities.
Is it just possible? I mean, with the original problem itself, equivalent binary. Instead of plotting both the orbits, plot one orbit with respect to the other orbit. That when you give the difference of the two, only to show that in real practical cases, when people observe binary systems, they always measure the distance of the other star with respect to the primary star. Okay.
Is that true?
Yeah. So because you don't have absolute system, you don't know.
No, I mean that is why we solve the equations. But you can always convert any two-body equation into a one-body equation.
No. What I'm saying is, suppose there are two binary stars going around each other. Okay.
Yes.
And when astronomers observe.
Yeah, but there we have an absolute system, right? Because that is given by our system.
No, but in the field of view of telescope, what typically amateurs would do is they will keep primary at the center and they will measure the position angle of the secondary. The point I wanted to, show it to people that even when you do this, the ellipse remains ellipse. So
sure. So let's try and do that. Okay. So let's see. Let's make again.
So while plotting, we can just plot difference.
Yeah. Exactly. That's what I'm trying to. That's what I'm trying to do. So let's do that. Okay. X best and Y best. Okay. So let's start again. Okay. So let's run that and let's see. There we
go. Right. So when we observe one elliptical orbit with reference to other elliptical orbit, it is still an ellipse.
doesn't look very nice. Yeah, you can make it a bit prettier. Anyway, yeah, you can. So you'll all get the Python notebook, so you can play with it yourself as well.
Yeah. So that primary is at 0, 0, and the secondary moves around that.
Yeah. Maybe we can also do the circle thing. And it's too big. Something like this. All right. So yeah, so that was about a binary system, and what we can do then is go to a trinary system. Okay? So here you have three masses, and you can think of this as, for example, you have a very heavy mass, say the Earth, a smaller mass, say the Moon, and a very small mass, like a satellite that you're trying to launch. Okay. So you have a trinary system that looks like this, and you can give certain x0, y0 values. So in my case, what we've done is the Earth is at 0, 0, the Moon is at 40, 0, and the satellite is nearer to the Earth than it is to the Moon. Okay, so it's at 10. And then you give certain velocities for the x and y components. So again, because I've placed all the objects only on the y-axis, I've only given them x velocities. Okay, so that's only just the horizontal velocities. And you do the same thing where you run over a range of time and you get this x and y values, and you can plot what the x and y components are for each of these objects. Okay, so right, so then in this case, green was the Earth, red was the Moon, and then blue is the satellite. Okay, so it's just exactly the same, except we are now doing it for the third system. So you can see that it's a fairly chaotic orbit of this satellite that we have with the given velocities. So it goes round and round in multiple ways, and sometimes it slingshots to a higher orbit. Okay, so yeah, all right. So you can play with this with as many number of particles that you want. I don't know if you can see, but at the center you see that there is a green dot, right? So that's essentially that is coming out because the Earth also moves very slightly with respect to these extra objects that are out there. Okay, so so this is something interesting that I want you to try out in the afternoon tutorials if you can, which is to try and simulate the trajectory of a rocket. So maybe we can just talk about it a little bit here. So when we so far what we've done is we've started with placing the particle already at a distance away from Earth and giving it some non-zero velocity, right? And then we say whether or not it is an escape velocity, whether or not it's enough to make an orbit, and so on. But of course, when we set satellites out into space and so on, we don't start from out there, right? We have to start from where we are on the surface. So so what exactly is it that happens? So what is going to be x0 and y0 in that case? So let's say x0 and y0 is so again, so y0 is the radius of the Earth, x0 is say 0. What is going to be the velocity that you start with? So you remember these launch videos of rockets? At the very beginning, what velocity does the rocket have?
The critical velocity.
Does it? Well,
No, ma'am. Critical is not there.
It
Starts
just
very
moves,
slow.
seems flowing very slowly. It moves. Right?
So the starting velocity is 0, right? It's just at rest.
Yes.
Then the burners ignite, and
Hello?
then slowly it starts getting some velocity. So what is happening here? So what is
Conservation of
happening is
momentum.
Sorry?
Momentum conservation, like with the changing mass, that formula we have, external force is equal to dp by dt, and the momentum is changing because the mass of the rocket is also decreasing.
Yeah, that is one thing, and it is also in the thick
And the
atmosphere.
velocity.
So this is so yeah. So there's actually a subtlety here, and what you're doing is you're converting the fuel to essentially you're burning the fuel to give you momentum,
That's
right?
what.
So it's not just that you're basically releasing some internal energy that is stored in the fuel by burning it. Okay, so that normally doesn't come up in our calculations when we do these simplistic calculations. We never take into account that you might be burning some internal energy and converting it into this motion. Okay, so one way to simulate this kind of problem would be to say that, so instead of just x and v, you maybe have some extra variable which you say call the amount of fuel in your fuel tank. Okay, and based on so your fuel tank gives you the same amount of acceleration until it is empty. That's a simplifying assumption that you can make. And then instead of just x and v, your acceleration depending only on x, or so in this case I'm just using x to mean all distances. You will have an additional component that comes from your fuel, and that is going to be an opposite in sign to your acceleration due to gravity. Okay, so you have a constant small acceleration until and unless until the fuel tank runs out, and you need enough fuel so that by the time the fuel tank runs out, you have achieved enough velocity to be able to escape the gravity of the Earth. So you would, if you want to simulate something like this, instead of having just 2 equations, you would have 3 equations. And your fuel equation basically is very simple. You just, so fuel is fuel minus some rate times dt. So if your rate is 1 unit volume per time, so it's just minus dt. And then at some point it just becomes 0. And then your acceleration will have this component from the Earth, which is just m by r squared with the minus sign, and then a plus component that comes from having some non-zero fuel. So that's just a constant term that is on as long as the fuel tank is not empty. Does that make sense?
Yes.
Yeah. So yeah, I think this is something interesting that you can try out, and yeah, don't worry about the moon and so on right now, but just try and see if you can figure out how rockets work.
Like if you have seen that rocket launch, the rocket bends at certain degrees at certain point in the sky. So is it also to reduce the load on the gravitational pull of the
No.
to the
So
rocket,
again,
or it is just to increase the velocity, like
very good question. So remember, when we placed your satellite at some x some y value, non-zero y value, the velocity that we gave it was in the direction perpendicular to the vector to the Earth, right? And that is what you need to achieve an orbit. If you just have vertical velocity, then as soon as the fuel runs out and it
will fall
will
like
go up
direct
till
free fall.
it will fall back down.
Yes.
Right, because there is nothing to give it a horizontal velocity. So at some point you need some boosters that will sort of tilt the rocket and then give it a horizontal velocity. So yeah, so that's a very good observation, and that's an important thing to know. So,
Ma'am,
yeah,
can
so
we
you will,
also like model the trajectory of the rocket from the base, like from the Earth, and
yeah.
calculate like at which angle it will like bend, and we get the trajectory from the surface of the Earth?
So at which
Like
angle it
we
will
do for the planets, can we do for the rockets also? Something in that.
Yeah, so actually the bending, I think is, yeah, it's not automatic as far as I know, that you need to have something extra that tells you when it will bend. So I think you will need to put it by hand if you want to do this. So what you can do is you can say that once the fuel tank is empty, just, yeah, so it will be slightly more complicated. You have to, or rather just before the fuel tank is empty, you have to give it your acceleration kick.
Bend or
Instead of being in the vertical direction, will be in the horizontal direction.
something.
And then you can see the orbit. So when it will bend, I'm not, yeah, one has to look up how exactly they do it. I don't know. There'll be some extra engineering that will be needed to understand this. What exactly
I think
causes.
one effect that probably, I don't know whether he's talking, is the thing that you observe on those screen. But that is partly because of Coriolis force also.
Yeah, I don't know. It might be possible, but I don't know off the top of my head what causes.
Because when you're giving velocity, that Earth's component of velocity is there. And as you
So
go to
that's
very high
a
height,
different thing.
so it will.
That is a different thing. That will cause the trajectory to move slightly in a different way. So it will not be straight up, but it will be something like this. But what he's saying is that instead of the rocket being vertical, at some point it also sort of tilts. Well, so I don't know whether that is automatic or whether they have thrusters that make sure that there is a tilt at the right time.
I think, ma'am, that must be an automatic. Like if you have know the Elon Musk, the rockets that Elon Musk is doing, it is fully computationally
Yeah.
operated from the base.
Yeah.
So I
So
think
it's automatic in the sense. So when you say automatic, that means that a human has designed it.
yes, in
Right.
short,
What we are
human
simulating in
also.
this,
Like human designs
what we're yes, but what we're simulating here in this notebook, there is the only human intervention is the initial velocity. After that, there is no human intervention. Right. So that is what I meant. So if you want to do this rocket tilting, then you need human intervention, maybe in terms of machine, computational programming, whatever, but it is a human intervention. It is not just gravity. So that was the difference.
I think if he's asking about why do they roll in the first place, then the roll program has a good explanation on Wikipedia. You could check that out. Why do they roll in the first?
Okay. So great. So yeah, you guys know more about this than me. But yeah, so if you want to, I just wanted to give you a toy problem to solve if you're interested in how to sort of send rockets out into space. Okay, so we're going to talk about the last topic for today, which is what are called Lagrange points. Okay, and so these points are certain points in configurations between two or more bodies, such that let's talk about the Earth, Moon, and satellite system. So a Lagrange point in this case would be a point somewhere in this system where the distance from that point to the Earth and from that point to the Moon always remains the same. Okay, so it's sort of like a fixed point in the system. So these kinds of points are really super important when you want to deploy certain specific satellites that do certain measurements or things like these. So so we're going to calculate two, or rather by trial and error, figure out two of the Lagrange points. Sorry. And then there are more. So if you Google Lagrange points on Wikipedia, you will find out all the Lagrange points that the system has, and you can try and figure out by trial and error how you can what velocity and distance configurations you need to stay in these Lagrange points. Okay, so so let me show you the plot first, and then we'll go to simulating this plot. Okay, so what is happening here is the green is the Earth, the red is the Moon as before, and the blue is the satellite. And you see that the trajectory that the satellite is following is that it is at the same distance between the Earth and the Moon at all times. Okay, so so this was just by so this is one of the Lagrange points where the distance from the satellite to the Earth and the satellite to the Moon remains same. So this is called L1 or Lagrange point 1, and it's usually between it's on the line joining the two heavier objects. Okay, so by now you know what the system looks like. You start with some x, y, vxy, vx0 and vy0, and then you iterate and you plot. So that's the same system. And so these are just some masses and velocities that I did by trial, and this is what you get. The one thing that I want to show you is, so the last component here is always the velocity of the satellite. Okay, the last component is always the satellite. So the x0 is 0, y0 is some value. But you will see here what is happening. So remember, if you're closer to the Earth, you need a higher velocity to stay in orbit, to stay in circular orbit, right? However, here you see that the stable velocity that you need is actually smaller. And the reason for this happening is that the gravity of the moon is also automatically pulling the satellite together with it. Okay, so if you remove the moon, so let's say if the mass of the moon is set to 0, then you see that the orbits are no longer stable. So the moon is still going around in a circular orbit, but the satellite is following some other orbit. Okay, so it started off with some velocity, but it was not high enough to give it a circular orbit. So it came closer to the Earth and then went far away again. So it's only when you have this heavy object that it works in this way. So that's that is the principle of the Lagrange point, that you have the gravity of the two objects balancing out, and so the light satellite that you place sort of remains in that reference system. It remains stationary. Okay, so this is very useful when you want to place certain satellites. So there's also a Lagrange point actually behind the moon. So you can place a satellite on at the dark side of the moon, for example, using this technique. And then, yeah, so then you will be shielded from all, say, radio transmissions from the Earth, because the moon will shield you. So you can have many other things like this. There's Lagrange points 4 and 5, which are essentially, so in that case, you have the moon and the satellite forming an equilateral triangle with the Earth. Okay, so these are more Lagrange points that you can try and discover. So yeah, so again, so there are certain values of x and y. So these values are calculated basically by just, so if you're the first particle is at 0,40, then you know the you know one side of the equilateral triangle, you know all the angles should be 60 degrees, so you can figure out what the other values of x and y should be, okay, for the third point. And then you can play with the velocities to figure out what is going to be the stable case. So you can see that the satellite is always 60 degrees ahead of the moon. Okay, so the moon is here, the satellite is here, and it stays 60 degrees ahead of the moon always. So it's again a stable configuration. So this is called, so there are two Lagrange points of this type, either 60 degrees ahead or 60 degrees behind the moon. They're perfectly symmetric. And so they're called Lagrange points 4 and 5. So there's a Lagrange point 2, which I told you is behind the moon. And there's a Lagrange point 3, which is essentially in the opposite direction to the moon. So if you like, you can try and figure out later, if you get time in the tutorial, you can try and figure out what the velocities and distances for those are. You can again plot these and you'll see that this is what it looks like. Okay, so I think this is mainly what I had planned for this morning's lecture. So if there are more questions, I'm happy to take them. Leave this here.
Ma'am, there are out of all Lagrange points, there are certain which are stable and which are unstable. So we can find out of which are stable and which are not.
No, so the Lagrange point is applied only to the stable ones. Okay. The name Lagrange point is given only to the stable points. Unstable points are not called Lagrange points.
Okay, ma'am.
Okay, more questions?
Yeah, there is one question here, Anchal. What are the limitations of simulations or models?
Right. So the answer to this question really varies depending on what your system is, right? So, for example, if you want to really send a rocket to a different planet or to the moon or whatever, your Newtonian gravity works perfectly well. So as long as your uh, mathematical uncertainties of your computational system are under control, that means you're not making an error with each iteration, then it works perfectly fine. But for example, you want to do something different, like you want to design a GPS system, then you cannot do this with Newtonian gravity alone, because the GPS system relies on the slight difference in time measurements that comes due to gravity. So this is a concept that that you will learn when you learn about Einstein's theory of gravity, which is a more complicated version and which simplifies to Newtonian gravity in certain limits. Okay, and for most of our everyday activities, Newtonian gravity is fine. But if you want to design a GPS system, a navigation system, then this is not accurate enough. Then you need to go to a different physics theory altogether, because the theory that you worked with was not accurate enough. So it depends really on what you're trying to do, uh, like whether or not the simulation that you have is accurate. So always what one does is one tests, you perform certain validations of your simulations with respect to systems that you already know well. So for example, so in the quantum mechanics class, we are going to try and simulate the hydrogen atom, and we can, so a simple simulation, what it will do is it will give us the relative levels of the of the system, relative energy levels of the system. So once you set say certain values, the mass, the charge, and so on, uh, you can then compare the energy, the transition energy levels that this calculation gives you, and you can compare it with a real life experiment. And you can ask, is your simulation really giving you something that compares with real life experiment? If it does, then you say your simulation is good. If it doesn't, then your simulation is not good. So always, whenever you do a simulation, you need to validate your simulation with some real life data. So this is true for everything, whether you want to do simulations in finance, whether you want to do simulations for disease progression, whatever. You might have a good model, you might not have a good model. Your model might work in certain cases only. So this is something that you can only find out when you compare with real life data.
There is also a question on whether quantum mechanics, but I think on 5th day you are discussing that.
Yeah. Yeah. Okay, good. So yeah, maybe I can stop
Okay, now
sharing
in this particular the gravity simulations, because I mean this was the one day. Now we'll be discussing other problems other days. How does one check for whether there are errors using this Euler's method we used, and how does one I mean, are there other methods that we will be discussing in next few days which will make it better?
Yeah, so we are not actually going to go beyond Euler's method, because I don't think it adds anything conceptually to have more complicated methods. But there are certainly, so there's for example, there is this Runge-Kutta method. If you want to go even more complicated, you have Gaussian integration methods and so on. So there are multiple methods that you can do to increase the accuracy of your calculation. If you want, I can provide you with names of what those are. But I think the Euler method is very nice in that it essentially looks exactly like what your differential equation looks like when you do pen and paper, right?
Okay,
So,
and one more thing within this method, like see for example, when you plot, you realize that the plot of the planet is not exactly following the same path. So there is a small drift, and it could be because of error. So
yeah,
are there ways, like one way I discussed yesterday, maybe you can calculate energy and see
Yeah.
whether energy is remaining constant. But are there ways to check within this
Yeah,
method?
so one of the things that you can do very simply is just changing the size of your time step and keep changing it till your answers don't change. So this is something that I often do. So this is called an adaptive time step algorithm. So you start with a certain time step and you get a certain answer, then you change your time step and you get a certain different answer, and you make your time steps smaller and smaller until your the difference between your solutions in the two cases is better than certain value, which is called a tolerance. So that is how much error will you tolerate, and this is again something that you set based on your requirements. Okay, so if you require so I mean, yeah, so for example, if you're drilling a hole from both sides and you want to meet in the center, then your tolerance is essentially the size of the width of your tunnel, right?
Right.
So that is, or rather, half the width of your tunnel. So did you expect to meet at least half of the tunnel over less, and then you can maybe make some adjustments.
Yeah.
But if you make your error to be very large, say 5 times the error of your tunnel, then you might be very far away. And
Right,
you will
and
never
without realizing.
So in this case, that sets your tolerance. So then you would rerun your simulation with smaller and smaller step sizes till you get the required tolerance that you can accept. The other thing that you should notice is has to do with essentially computation. I mean, computer science, not really physics, which is how what is the smallest number your machine can represent accurately. So these are what are called floating point errors. So remember, your computer works only in zeros and ones, right? So when you're writing 0.001, what your computer is doing is there is I forget the technical name, a representation of this 0.001 in terms of zeros and ones. And there are many different kinds of representations. And what we often use, all these codes use, are what are called floating point representations. And based on the number of bits you allow for a single number, that will tell you how accurate or inaccurate your floating point representation is in terms of these zeros and ones. So it sometimes helps if you can go to a more accurate representation. So like for int, if you use 8 bytes, you can use long int, which is 8 bytes. I forget. But you can go for long int, which is twice as many zeros and ones to represent the same integer. And then you can have more integers, right, with long int. So similarly for float, if you have a float, which is some X number of bits, you can have a double float, which is often just denoted by double, which is twice the number of that. So I think Python by default uses double precision. So this is called double precision. It uses double precision for everything. But you can have quad precision, which is 4 times the standard floating point representation, and so on. So yeah. So this is a different side of precision, which is to do with computer science rather than physics.
Yeah, and one more question I have, now that you showed the very interesting simulations on calculating Lagrange point, is it possible, on one of the days, to show how to plot equipotentials or those kind of things?
Right. Okay. Let's see. So
If
I'll
time
write it
permits,
down.
or maybe
Yeah, I mean the plotting is not difficult. So
because
there's
that
always
algorithm thinking equipotential is something.
For equipotential, okay. Yeah. So I'll tell you in words how you do this. So what you would do is you would say your system is between x plus and minus 100 and y plus and minus 100. For each x and y, you would calculate. So equipotential only makes sense at a single time value, right? You are taking a snapshot of the potential at a single value of time. So let's say it's time t equals 0. You have two masses wherever you want to place them. What you would do is you would go around scanning from minus 100 times minus 100 times plus 100. That's your upper left corner, all the way to 100 comma minus 100. That's the bottom right corner. So you would scan each and every point, and you would calculate what the potential is. And then what you would do is what are called contour plots. So we can have an example of this, for example. And the contour plots, so this is built in Python, and the contour plots will plot contours of equipotential, essentially.
Okay, thank you. So maybe we'll explore that in the tutorials.
Yeah, it should not be very difficult to do. Yeah, if you had thought of this earlier, I would have had an example already.
There are no more questions, so we can continue tomorrow.
Yeah, okay. Yeah. Okay, then thank you all, and see you tomorrow.
Yeah, thank you.
Thank you, ma'am. Thank you so much.
Thank you, ma'am.
Thank you.